So good morning, everyone. Today we are going to discuss about the chapter 7, P block elements. Okay, P block elements. So which are the P block elements, or which are the groups that comes under this P block elements? Yes, anyone?
13 to 18.
Yeah, 13 to 18. From group 13 to group 18, right? So these are the P block elements, and this chapter we will learn 13 to 18. And we will learn more about group from group 15 to 18. Okay, we are skipping this group 13 and 14. We will start with group 15 elements. Group 15 elements. So among this P block elements, group 18, it's very important, noble gases. Then group 17, they are halogens. Group 16, they are chalcogens. Then group 15, that belongs to the nitrogen family. Okay, so we will start with group 50. So these are the elements present in group 50. Nitrogen, phosphorus, yeah.
Ma'am, in this chapter, the deleted portions can say.
Only a small portion. That's page number 180. Starting from phosphorus. Page number 180. Starting from phosphorus, then phosphine, phosphorus halides, oxoacids of phosphorus. These are the only deleted portions.
Okay, ma'am.
Okay. Yes. So the P block elements, in P block elements, group 15 consists of nitrogen, phosphorus, antimony, bismuth, arsenic. 1 minute. Yeah, one more there. That is moscovium. Okay. Moscovium. That's a radioactive element. Clear, children? Nitrogen, phosphorus, antimony, bismuth, arsenic, moscovium. Okay. So these are the elements present in group 50. Nitrogen, it's atomic number 7. Phosphorus, it's 15. Arsenic, 33. Antimony, 51. Bismuth, 83. And this moscovium, that comes under, I think the more details about this moscovium is not yet published, because in the case of this radioactive elements, they will be obtained from nature in very small quantities. Okay, so that very small quantities is not enough to learn about the more properties of that element. So the properties of this radioactive element moscovium, it's not yet completed about its studies. So these are the elements present here, and about their configuration, they have a common configuration NS2 NP3. NS2 NP3. Their s orbitals are always completely filled and p orbital is half filled, making their electronic configuration extra stable. You know that in the case of p orbital, the maximum number of electrons is 6, right? Maximum number of electrons is 6. Here it is 3. That means it is half filled. It's half filled, right? So it has one extra stability. S shell is completely filled, P shell is half filled. So these group elements have extra stability. Okay, then we are moving to the occurrence of these elements. Occurrence of these elements. So first one about nitrogen. Here you can see in page number 170 the occurrence of each element that comes under this group 50. First one about nitrogen. Nitrogen is available in the form of sodium nitrate, NaNO3, then KNO3. These are the two forms of nitrogen in nature or earth crust. Okay. First one sodium nitrate, second one is potassium nitrate. And it is always found in plants and animals. Proteins of plants and animals. Then next one about phosphorus. In the case of phosphorus, it will be available in nature in the form of certain rocks. Phosphate rocks. Phosphate rocks. Then, yeah, it's a main constituent of animal and plant matter. It's a constituent of animal and plant matter. It's available in bones also, right? Phosphate. So these are certain sources of phosphorus. Then about this arsenic and antimony, bismuth. Arsenic, then antimony, bismuth. These three elements, they are found as sulfide minerals. Okay, sulfide minerals. Clear, children? Then in the case of this moscovium, I told you it's a synthetic radioactive element. Moscovium, it's a radioactive element. So its properties are not completely discovered. Okay, moscovium, it's a radioactive element. So that's about the occurrence of different metals. Its symbol is Mc. Atomic number 150. 150. Yes.
Should we learn the electron configuration of all these elements?
Please try to learn the general configuration and try to learn the configuration of the lower members of this group. Okay. Like nitrogen, phosphorus, like that.
Okay.
Okay. Then we can discuss the MCQ questions, and if there is any chances for such questions, we can practice that. Okay.
Yeah.
Yes. So in the case of this radioactive element moscovium, it will live for a very short time and very little quantity will be obtained from nature. That's why the complete study of this elements is not possible. So that's about the occurrence. Nitrogen, it's from sodium nitrate and potassium nitrate from nature, and from the plants and animals, the protein content, it's made up of nitrogen. In the case of phosphorus, it's from phosphate rocks and it's a constituent of animal and plant matter. It's also obtained from bones. Then in the case of arsenic, antimony, bismuth, they are obtained as sulfide minerals from nature. Moscovium, it's a radioactive element. So that's about the occurrence of these metals, elements. Okay. Next one, we are moving to the properties. Electronic configuration that we already discussed, that is ns2 np6. S orbital is completely filled, p orbital half filled. That's why they are extra stable. Then in the case of size, no need to learn the entire thing. In the case of atomic and ionic radii, okay, atomic and ionic radii, it will be increases down the group. From nitrogen to phosphorus, this atomic and ionic radii, it will increases. Okay. From nitrogen to phosphorus, considerable increase in the covalent radius. That means size also increases. Then from arsenic to bismuth, there is a small change in the increase of radius. From arsenic to bismuth, small increase in the radius. Okay, nitrogen to phosphorus, atomic radius, covalent radius increases. From arsenic to bismuth, only small increase in its radius. That's about the atomic and ionic radii. Next property is ionization enthalpy. Ionization enthalpy. So you know that normally this ionization enthalpy, it will increases from left to right in a periodic table, and it will decreases from top to bottom, right? So here also this ionization enthalpy, it will decreases down a group from nitrogen towards the end of the element in this group. This ionization enthalpy, it will decreases. Okay, children, ionization enthalpy decreases down the group due to the increase in atomic size. The reason is that increase in atomic size. What is ionization enthalpy? The energy required to remove the electron from the outermost shell. Okay, so in the case of this p block elements in a group, this ionization enthalpy decreases. Then the next property, that's about electronegativity. Electronegativity. The most electronegative element is considered as fluorine, right? In group 70. So when we moving down the group, the same thing, this electronegativity also decreases. Electronegativity decreases down the group with increasing atomic size. Here also the same reason, increase in atomic size. Okay, so we discussed about atomic and ionic radii, ionization enthalpy, electronegativity. Then next we are moving to the physical properties. Physical properties. Yes, physical properties. So all the elements of this group are polyatomic. All the elements of this group are polyatomic. They are available in the form of such type of molecules, not as atoms, single atoms. They will be available in the form of polyatomic molecules. That's it. Then this dinitrogen, N2, it's a diatomic gas. All others are solid. Phosphorus, arsenic, antimony, all are available in the form of solids. Nitrogen is a diatomic gas. Then this nitrogen, okay, then in the case of these elements in the group 15, nitrogen and phosphorus are non-metals. Okay, nitrogen and phosphorus are non-metals. Arsenic and antimony are metalloids. Nitrogen and phosphorus, non-metals. Arsenic and antimony, metalloids. Bismuth is a metal. Bismuth is a metal. And in the case of moscovium, its properties are not completely studied. Then except nitrogen, all other elements show allotropic nature. What is allotropic nature? They can be exist in different forms. If you are thinking about carbon, they can be exist in the form of coal, diamond, graphite, etc. These all are allotropic forms of carbon. Similarly, except this nitrogen, all other elements in group 15, they will show this allotropic nature. Phosphorus exists in different forms. Okay. Similarly, arsenic, antimony, bismuth, etc. So that's about the physical properties of metals. And one more, physical properties of the elements in group 15. One more thing about the boiling point. Okay, in the case of this boiling point, it will increases from top to bottom. Boiling point, it will increases from top to bottom. But in the case of melting point, it will increases up to arsenic, then it will decreases. Melting point increases up to arsenic, then decreases up to bismuth. Clear, children? So these are the certain physical properties. All the elements of this group are polyatomic. They cannot exist as an independent atom. Dinitrogen, it's a diatomic gas. Others are solids. Okay. Then nitrogen, phosphorus are non-metals. Arsenic and antimony, metalloids. Bismuth is a metal. So except nitrogen, all other elements shows allotropic nature. Then we are moving to the chemical properties, and the first one, oxidation states. Okay, oxidation states. So mainly this group 15 elements, they will show a common oxidation state, that is -3, +3, +5. These three are the common oxidation state shown by this group 15 elements. -3, +3, +5. And the tendency to exist in -3 oxidation state, it will decreases down the group due to increase in size and metallic character. So the tendency to exist in -3 oxidation state, it will decreases down the group. That means nitrogen shows more tendency to exist in -3. Then we are moving down the group. This tendency to exist in -3 oxidation state, it will decreases. Clear? The reason is that increase in size and metallic character. Increase in size and metallic character. And in the case of bismuth, it's a last member of this group, right? Just before moscovium. So bismuth hardly shows -3 oxidation state. It's very difficult to show -3 oxidation state by bismuth, because I told you when we are moving down the group, this -3 oxidation state, the tendency to exist in -3 oxidation state, it will decreases. Then the stability of +5 oxidation state, it will also decreases down the group, and that of +3 oxidation state increases. So in the case of -3 and +5, the tendency to exist in these two oxidation state, it will decreases, and this +3 oxidation state, it will increases. Clear, children? -3 and +5. The tendency to exist in these two oxidation state, it will decreases down the group. but the tendency to exist in +3 oxidation state, it will increases down the group. We are always comparing the properties of elements from top to bottom. Okay. Clear, children? Is this clear?
Yes, ma'am.
Okay. So it is due to inert pair effect. What is this inert pair effect? I told you about their electronic configuration, right? In the s orbital, they are completely filled, right? ns2, np3. That's the general configuration. So, yes, yeah,
Ma'am, this part is not clear now. Like -3 +3 +2.
I will repeat it. Wait. So here is the reason is that inert pair effect. Okay, inert pair effect. Inert pair effect is that the configuration is ns2, np3, right? That means s orbital is completely filled. Due to the completely filled s orbital, they will not take part in chemical reaction. They remain inert. Inert means they do not involve in chemical reactions. So due to this inert pair effect, the tendency of +5 oxidation state and -3 oxidation state, it will decreases down the group. Okay, Achud, look here. In the case of elements in group 15, starting with nitrogen, phosphorus. 1 minute, children. Okay, arsenic, then antimony, bismuth. This is the order, right? So when we are moving down the group, the tendency to exist in -3 oxidation state and +5 oxidation state, it will decreases. Clear? Okay. Then in the case of +3 oxidation state, the tendency to exist in +3 oxidation state, it will increases when we are moving down the group. The reason is that inert pair effect. The s orbitals do not involve in chemical bonding. So there will be more tendency to exist in +3 oxidation state when we are moving down the group. Clear? Okay, that's it. So the only well-established +5 oxidation state is bismuth, that is BiF5. I told you bismuth is the last one when we are neglecting this moscovium. So in the case of bismuth, it will be very difficult for this -3 and +5 oxidation state to occur in bismuth. Only possible +5 oxidation state in bismuth is BiF5. Clear? Shall I move to next one, children? Yes or no?
Yes, ma'am.
Yes. Next one, what do you understand by inert pair effect? I already explained the non-participation of inner line 2s electrons in the bond formation. It is known as inert pair effect. The inner lying s electron pair does not participate in bonding and acts as an inert pair. Because of this effect, tendency to lower oxidation state increases down the group. You just know the reason, that is inert pair effect. And inert pair effect is that the s orbitals do not involve in bonding because they are completely filled. That's needed.
Ma'am,
Yeah.
like, actually, what are +3 -3 we are discussing here?
Oxidation states. How can we write the oxidation state? When they involved in chemical bonding, sometimes we will calculate the total number of electrons present in the outermost shell, right? Otherwise, how many electrons are required to become 8 electrons? So it will be changes when they are reacting with each elements.
And so we are talking about valence here.
Yeah, same thing. Valency and oxidation state, same. Nowadays, we are using oxidation state other than valency. Both are same. So due to this inert pair effect, this tendency of +5 and -3, it will decreases down a group. Then next one, nitrogen is restricted to a maximum covalency of 4. The maximum covalency or maximum oxidation state shown by this nitrogen, it will be 4. What's the reason? Because only 4 2s and 3p orbitals are available for bonding. That's the reason. When we are writing its configuration, it is 1s2, 2s2, then 2p3, right? Yes, 2p3. So only 4 2s and 3p orbitals are available for bonding. That's why the maximum covalency of nitrogen is restricted to 4. It will not show other oxidation states. Why the covalency of other elements of group 15 can be increased beyond 4? Because they have vacant d orbitals in their outermost shell. When we are moving down the group, you know that additional shells will be added, right? Additional shells will be added. So there will be d orbitals there. So due to the presence of vacant d orbitals in their outermost shell, the elements other than this nitrogen, it will show oxidation state beyond 4. That is plus 4, plus 5, like that. Clear? Clear, children? Yes or no?
Yes.
Okay. Next one. Why and how does nitrogen shows anomalous behavior? When we are comparing the elements in the group 15, this nitrogen shows anomalous behavior or different properties compared to others. The reasons are there. Their small size. Okay, their small size, high electronegativity, high ionization enthalpy, then non-availability of d orbitals. These are the reasons. Here you can see the heading, anomalous properties of nitrogen. Okay, anomalous properties of nitrogen. So here, small size, then high electronegativity, because when we are moving down the group, electronegativity decreases. And high ionization enthalpy. In the case of ionization enthalpy also same thing. It will be decreases down the group. Okay. Then non-availability of d orbitals. In the case of nitrogen, there will be no d orbitals. 1s2, 2s2, 2p3. That's the only orbitals available. And it has a unique ability to form p pi p pi bonds. P pi p pi multiple bonds. In the case of nitrogen, you can see that nitrogen will be existing triple bond, right? Triple bond. So due to this triple bond, always we will draw this pi bond for double bond or triple bond and sigma bond for single bond. I think you have learned the same things in the plus one, right? Sigma bond, it is due to the presence of single bond, and pi bond, it is due to the presence of multiple bonds. So comparing with phosphorus, arsenic, antimony, bismuth, here nitrogen will show triple bond. So due to this, it will form p pi multiple bonds with itself and with other elements having small size and high electronegativity. So this is another property of nitrogen compared to other elements in this group. And their catenation tendency is weaker in nitrogen as compared to other elements of this group. What is this catenation? Catenation. You know that in the case of carbon, we can, it will be formed a very long chains like this, right? This type of long bond formation that is known as catenation. Catenation. Okay, organic compounds are all based on this catenation property. Long chains of same element, that is catenation. So this nitrogen has very weaker or very less tendency for this catenation compared to other elements in the group. So these all are the different properties of nitrogen compared with other elements, their anomalous properties. Clear, children? Emmanuel, can you please read the points?
It has unique ability to form p pi multiple bonds with itself and with other elements having small size and high electronegativity. Catenation tendency is weaker in nitrogen as compared to other elements of this group.
Okay. So shall I move to next one, children? Okay. Yes. So next, why the heavier elements of group 15 do not form p pi bonds? I told you in the case of nitrogen, it has a tendency to show p pi bonds, but other elements did not show this p pi bonds. because their atomic orbitals are so large and diffuse that they cannot have effective overlapping. You know that due to the overlapping of orbitals, there will be double bond or multiple bonds formed, right? Sideways overlapping and lateral overlapping. So in the case of this heavier elements compared to nitrogen, their atomic orbitals are very large and diffuse. They cannot make effective overlapping. So it cannot able to form multiple bonds. Then why is the single bond in nitrogen much weaker than single bond in phosphorus molecule? Because of high inter-electronic repulsion of the non-bonding electrons owing to small bond lengths. Because of the above reason, catenation tendency in nitrogen is much weaker as compared to other elements of this group. I told you about nitrogen. It will not show heavier tendency to show catenation. Catenation means the long chain of nitrogen. Okay, long chain of nitrogen. The reason is that because of high inter-electronic repulsions, there will be a repulsion between the electrons present in the non-bonding electrons. Non-bonding electrons means lone pair of electrons. Electrons that do not involve in chemical bonding. There will be inter-electronic repulsion of the non-bonding electrons owing to small bond length. So due to this repulsion, their bond length will be reduced. So because of this reason, catenation tendency in nitrogen is much weaker. But in the case of phosphorus, it will shows such a catenation property. The catenation tendency that is more for carbon. That's why so much organic compounds are formed. Okay. That's about the anomalous properties of nitrogen comparing with other elements. Then we are moving to the reactions. Reactivity towards hydrogen, oxygen, halogen, metals. Okay. So first one, reactivity towards hydrogen. Reactivity towards hydrogen. So this group 15 elements form hydrates of the formula EH3. E stands for element in the 15th group. Okay. E stands for the element in the 15th group. Then H for hydrogen. So all elements in this group 15, they will show the same hydrate. That means with the formula EH3. Example, NH3, then PH3, that is phosphine, then ARH3, like that. So this is the general formula. E stands for the elements in the group 15. So group 15 elements form hydrates of the formula EH3. Example, you can write NH3, where E is the element of the group 15. And this hydrates show regular gradation in their properties. That is, stability decreases from NH3 to BiH3. So this is the order BH3. Then last one BiH3, bismuth. So the hydrates show regular gradation in their properties. Their properties will decreases from nitrogen towards bismuth. Their stability decreases from ammonia towards bismuth hydride because of the decrease in bond dissociation enthalpy. What is bond dissociation enthalpy? The energy required to dissociate the bond into ions. That is bond dissociation enthalpy. It will decreases from nitrogen towards bismuth. Okay. Then the reducing character of hydrates, it will increases. Reducing character of hydrates, it will increases. That is NH3, it's a strongest reducing agent, while BiH3 is the weakest. You know that reducing agent and reduction, these two terms are just opposite to each other, right? Reduction means they will lose electrons, right? They will lose electrons. And the reducing agent, that the agent helps in reduction. That means the opposite thing happens in this reducing agent. Okay, so this reducing character of hydrates increases means nitrogen will be lesser reduced compared to bismuth. So nitrogen is a better reducing agent. Clear? This is clear, children? Reduction and the reducing agent, they are opposite terms. Reducing agent, the agent helps in reduction. That means oxidation will happen in that substance. So in the case of this nitrogen, it is a better reducing agent. That means strongest reducing agent, That means it will reduce other substances and oxidation happens in nitrogen. So you can learn that reducing character of hydrides increases from ammonia towards bismuth, bismuth hydride. That's it. Clear, children? This is clear?
Yes.
Okay. Then next point, that is pH3, that is phosphine. It has a lower boiling point than NH3. pH3 molecules are not associated through hydrogen bonding in liquid state. Always the reason for boiling point, that is hydrogen bonding. We have learned it in the case of alcohols, phenols, etc. Do you remember that? The same thing here. In the case of NH3, there will be a tendency for hydrogen bonding. Okay. But in the case of pH3, it has a very lower boiling point because they are not associated through hydrogen bonding in liquid state. That's the reason. The case of melting point also, it will be higher in NH3. Okay, boiling point and melting point both are greater in NH3 compared to pH3. Then the basicity decreases in the order. NH3 has the maximum basicity, then it will be decreases pH3. Then, sorry children, for arsenic it is AS. I think the previous also I write AR. It is AS, sorry. ASH3, then SBH3, then BiH3. This is the order of their basicity. Clear? That's about the reactivity towards hydrogen. Reactivity towards hydrogen. Then shall I move to next one? Tell me.
Yes, ma'am.
I know that there will be some difficulty. I'm just rushing through all these portions, but we can revise it well. Okay, we can start with the revision of P block elements. Don't worry. Okay. Yes. Next one about the reactivity towards oxygen. Reactivity towards oxygen. Here they form two types of oxides. Okay, two types of oxides. They have a general formula E2O3, E2O5. You can write down the examples. N2O3, then N2O5, P2O3, P2O5, like that. So E represent the elements in the group 15. The oxide in higher oxidation state, E2O5, it will be more acidic. The oxide in higher oxidation state, E2O5, it is more acidic. Then their acidic character decreases down the group. When we are moving from nitrogen towards bismuth, this acidic character decreases. Okay, acidic character decreases. Then the oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That means N2O3 and N2O5. Sorry, N2O3 and P2O3, they are purely acidic. N2O3, then P2O3. They are acidic. Then arsenic and antimony, they are amphoteric. Amphoteric means they will react with both acids as well as bases. Okay, that is amphoteric. So in the case of arsenic and antimony, they are amphoteric. As2O3, then Sb2O3. These two are amphoteric. And the remaining bismuth, that is basic, Bi2O3, that is basic. That's about the reactivity towards oxygen. They form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state, that is E2O5, that is more acidic than E2O3. And this acidic character will decreases down the group. Then oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. Arsenic and antimony amphoteric. Bismuth basic. Then the next one, there is reactivity towards halogens. Okay, reactivity towards halogens. And here also there is one common formula, EX3, EX5. X stands for any halogen. So we can write N, okay, PCl5, then PCl3. This can be one example for this type of compound, right? Element with element that comes under group 50. And we can write any halogen, PBr3, PBr5, like that. So in the case of this nitrogen, it does not form pentahalide due to non-availability of the d orbitals in the valence shell. Nitrogen does not form pentahalide. That means it cannot form NX5, NX5, because it does not contain d orbital. That's the reason. Then the next topic, next point, pentahalides are more covalent than trihalides. Pentahalides are more covalent than trihalides. That means in pentahalides, there will be more sharing of electrons. In pentahalides, sharing of electrons. Then in trihalides, it will be less. Okay, sharing of electrons will be less. All the trihalides except nitrogen are stable. All the trihalides except nitrogen are stable. NF3 is the most stable trihalide of nitrogen. Okay, all the trihalides except nitrogen are stable. Then NF3 is the most stable trihalide of nitrogen. The halides except BiF3. BiF3 stands for bismuth fluoride. It is covalent in nature. Trihalides except bismuth fluoride, it is covalent in nature. So that's the reactivity towards halogen. Their general formula EX3 and EX5. The nitrogen does not form pentahalide due to non-availability of d orbitals in the valence shell. When pentahalides are more covalent, that means more sharing of electrons take place in pentahalides than trihalides. Then all the trihalides except nitrogen are stable. And among this different trihalide of nitrogen, NF3 is the most stable. And trihalides except BiF3 are covalent in nature. Okay. Then the next one is reactivity towards metals. Here also, these elements react with metals to form their binary compounds exhibiting -3 oxidation state. I told you about 3 types of oxidation state. That is +3, +5, -3. When they are reacting towards metals, they will show -3 oxidation state. And these are the examples of compounds they are reacting with metals. Ca3N2, calcium nitride. Then Ca3P2, that is calcium phosphide. Then Na3AS2, sodium arsenide. Okay. So that's about the reactivity of this group 15 elements towards metals. Clear, children? Okay. Then the next portion, that's about dinitrogen, its preparation properties. Then ammonia, its preparation properties. Then nitric acid. Here, one small portion, oxides of nitrogen, that's not mentioned in the syllabus, but we need to just go through that. Then nitric acid, its preparation properties. That's for the group 15 elements. Okay. So we can discuss the remaining about nitrogen, ammonia, nitric acid in the next class. Then the group 15 elements will be completed. I told you phosphorus portion, that's deleted. Okay, then we can move to group 16. Okay. Okay, children, all of you read this portion very well in the textbook. I think most of the important points are mentioned in the slide. If you need slides, I will share the daily slides to one among your classmates. Okay, then you can share it with everyone. Clear, children? Yes. Okay. All of you switch on your videos. Let me take your attendance. Just wait. Okay, all of you, please go through the portions in the textbook. Then if you have any doubt in any point, you can ask me. Okay. Otherwise, it will be very difficult when you revise the entire portion together. So you can read this portion daily. Clear? You can see that each line is important here. We cannot skip any line. So we can expect more MCQ questions from this chapter. So try to learn this portion very well in the day itself. Clear, children? Yes. So thank you very much. See you in the next class. Bye.